Welcome everyone, I'm Gabor Szappanos, malware researcher at Sophos. Let me tell you a couple of words how I ended up with this presentation. I joined Sophos last summer when Sophos opened a new development office in Budapest, and at that time, actually I joined with quite a lot, almost all of my colleagues from the former Virus Buster team. And soon after joining, I started working on a research project that involved analysis of APT attacks, the targeted attack samples. More precisely, I was working on samples that involved document exploitation in the execution scheme. And this is how I ended up at the end with this presentation, which will focus on shellcodes using in targeted attacks. If you have been here yesterday, Baldy's presentation, he had a roundup of the APT attacks of the last year. You will see a couple of familiar names in this presentation. I picked up as examples the high-profile targeted attacks from the past year. So, and one forward. 4 years ago, here at Hacktivity, there was already a presentation about shellcodes. But I will be very generous with the audience, and I won't assume that you remember most of the presentation. Furthermore, I'm even more generous because I won't assume that you remember anything of that presentation. So if you weren't there or you're not familiar with the shellcode, I will start from the very beginnings, and at the end, hopefully you will understand more and more of it. So, why is this interest in the shellcodes? Why the shellcode is that important? Let's see a typical targeted attack scheme. We have a happy, uninfected computer. An exploit document arrives to this happy computer. Some black magic happens in the background, and the final result will be an infected computer when a malware is running on it. So this black magic that happens in the background is the shellcode. So in the beginning, the computer is intact. At the end, the computer is running some Windows Trojan. And you know, at the point that your computer is running a Windows Trojan, it's not your computer anymore, it's their computer. So the transition from my computer to theirs computer is exclusively done with a shellcode, which is executed after the vulnerability is triggered in this document. So the shellcode is a critical, crucial component of a targeted attack, which takes over the computer. So, but fear not, this silly graphics is not the direction this presentation is going to. So let me just balance it with a demo. A brief intro into document exploits. Now, those of you who were here last year on my presentation may remember this highly sophisticated device I used in my demo there. In fact, this is an enhanced version of that one, but nevertheless, I'm not prepared to use these demos. I have prepared for you a couple of demos involving virtual machines. With a single intent that if a presentation, you can see that the presentation is highly technical and deep if there are demos running virtual machines in that presentation. So I wanted to give a very technical and deep presentation. And that was a little additional reason that I'm going to run live virus samples, and I just don't want to ruin my personal laptop with running a virus sample on it. So that's why demos are executed in virtual machines. So let's start our first demonstration. This demonstration will just show you in brief and in an overall overview how document exploitation works on a computer. For that, I picked up a malware that was not present yesterday, nevertheless is one of the most active malware groups known nowadays which are using document exploitation. It's from the plugix malware group. It is using the The CV 2012-0158 exploit, which was mentioned yesterday in practically all of the exploitation cases and all of the high-profile targeted attacks. The host document that hosts the exploit is an RTF document, is a text represented document. It starts with the carrier part, then an embedded ActiveX object is found in the document. This is where the exploitation happens. It could be, it could be one of the tree view or syslist view control ActiveX objects that are embedded into the document. It starts as a binary embedded blob here. And shortly after that, when a condition occurs, here is the beginning of a shellcode that will be later on executed. If we scroll even further down the document, we will see that at some point, right around here, the text stops in the RTF, which is quite a surprising fact, given that this is a text document format, and some binary data is embedded into the document. This will be the final Windows executable payload Trojan that is executed on the infected computer. So what's happening in the background? We will fire up a virtual machine to investigate that. In the virtual machine, we are going to start a simple API spy program. It is a Sophos developed tool, but you can use any of the free available tools like Epimonitor from Rohitab, whichever that gives you a list of API calls, Windows function calls, which were executed during execution of a process. Now, using this framework, we are going to spy on the invert exe. So we are going to start just that. And once we are done, we execute it. A lot of internal housekeeping things start happening in Word, and we can start using it. I could have activated this copy of Word, but it will have an interesting side effect not doing it, and you will see it briefly why I choose not to do that. So I open the infected document. And it's opened. And what you are seeing is that document content is displayed on the screen. Moreover, you will see another activation prompt, which will just give you out the detail that this document content was opened in a second instance of Word. So a new instance of Word was created. So let's see what was happening in the background. In the background, what was happening is that the old instance of Word was exited. A file named dw20dll was dropped on the system. This file name really mimics the file name used by the Dr. Watson utility, which is often executed on a system if something crashes. This DLL itself is a dropper. It drops 1.tmp, which is a Trojan on the system. And sometimes later on, it is executed, this dropped executable. So what you can see from this picture is that whenever you open an exploited document and the shellcode runs, the old instance of Word is closed. DLL file dropper will be created and executed on the system. And in the background, a decoy document will be displayed just to distract the user's attention after all, he was expecting to open a Word document, so it would be pretty suspicious if the Winchester starts spinning and nothing is displayed. Even more interesting is what we could not see in the activity log. We could not see the execution of the dropped DLL file, and we could not see the creation of the second Word exe instance, which displayed the decoy document. But halfway into this presentation, we will understand why it happened. So let's skip back to the slides. Like any other entity, it has to answer a couple of big questions of life, like where am I, where did I come from, what am I going to do? These are the big questions the shellcode has to solve. And these are really the three main steps of execution that every shellcode has to perform, at least the ones involved in document exploitation schemes. Let's see the first one, where am I? The question in this case that the shellcode has to determine its own memory position. You remember it started executing due to some memory corruption somewhere on the stack on an unpredictable location. So it has to know its own location for a couple of good reasons. First of all, in most of the cases, the rest of the code is encrypted. It has to decrypt itself. In order to decrypt itself, it has to know where its bytes are lying in order to decrypt them. The decryption is done for a couple of reasons. One of the reasons is that this way the main shellcode content is hidden from analysis. The other is that in normal Win32 codes, there are a lot of 0 bytes because it uses small integer variables which are stored in a D word, so there are a lot of zeros in it. Now, in exploitation, in most of the cases, it is some string buffer overflow. And in string buffer, zeros are terminator characters. So if a shellcode doesn't avoid using zeros in its code, then the problem will be that after the exploitation, the rest of the shellcode after the first zero will not be executed. So this has to be avoided. And in some cases, a shellcode has to use some initialized internal variables, internal memory variables, which are stored along with the code, like the embed bit executable length and offset, or the decoy document length or offset. It has to access these variables. In order to access them, it has to know the memory location of them. So how does it find the memory location? One of the methods, actually it is used in the Red October campaign samples, is a classic call pop construct. At the start of the execution, the code jumps to this location and immediately calls back to the init of the loop. Now, when a call instruction is executed, sorry, I don't want to embarrass the audience by these trivial assembly topics, but I'm not aware of your skill set. So if it is boring to you or it's just too nagging, just tell me and I'll skip that one. So anyway, when a call is issued, the address of the next instruction is pushed on the top of the stack so that the processor would know where to return when the called function is terminated or finished, where to return. So with this call, the address of this instruction is pushed on the top of the stack, and right after that, it is popped from the top of the stack. So at this point, in the EBX register, we have the absolute memory address of this line, of this memory location. And from that on, the shellcode knows exactly where it is lying in the memory. It can start to decrypt using this pointer with the simplezor cryptor. It's a nice and classic method. It's been used for ages. Like from the very first Windows file infector viruses already use this scheme to to find their own exact memory location. Also, it's been used at least for 10 years in the executable crypto, so it's not nothing new. Another method for finding memory location was used in the IceFog APT campaign. It was just published this campaign was published just a couple of weeks ago. It gets the memory location using the floating point environment. How it works is that at some point of the execution, it issues any random FPU instruction, and at some point later queries the floating point environment. This FNSTF instruction just stores the floating point environment structure on the specified location, which will be somewhere on the stack. So if you're looking up at the Intel documentation for this instruction, you will see a detailed and exact description how it works. It fills up the fields of a memory structure. It is detailed, but it's totally useless if you want to understand how this actually works. So for that, you will need a format specification, which also includes the offsets of the internal fields of these structures. From that, you can see that the only interesting field in this structure is the IP offset, which is at offset C in this structure. This offset holds the EIP register value at the time the last floating point instruction was executed. So if I skip back to this code, the environment is stored 12 bytes behind the stack. So when it is stored there, at the top of the stack will be the EIP value. It is popped into the EBX register. The EIP value will be the memory address of the last executed floating point instruction, which will be the address of this one. So at this point, the code already knows its location. It can start the decryption loop using indexing with this register from that value. It's a very nice method. It has been used for a couple of years, but it's very common knowledge. Most of the Metasploit Shellcode payloads are using this method for getting the EIP. So there's really nothing original in it. Another, at least partly original method is used by the FAKEM campaign. In this case, the shellcode will, the EIX register is filled with the stack pointer, and it will start a search on the stack for the 33 hex byte. So what the search will do is start from here and go down until the very start of the shellcode is found. Now, to use this shellcode, to use this method, the shellcode has to be sure that the stack pointer will point somewhere nearby the beginning of the shellcode. Otherwise, there will be a chance that some random bytes will be picked up from the memory. Anyhow, this is another method for accessing the location. The next more interesting question is, what am I going to do? So at this point, we have a shellcode that has decrypted itself on the system. It may execute some very complicated mathematical algorithms. It can add up numbers, it can multiply numbers, but obviously that's not what the shellcode wants to do. It wants access to the system. It wants access to the system services. For that, it needs access to the Windows functionalities, the Windows API functions. Now here comes a little problem. The Windows API function addresses are not available for the shellcode. It's just a block of code executing somewhere on the stack. It has zero knowledge about the Windows DLL functions. On some other operating systems, these functions would be easily available. For example, on DOS, there is the hex21 interrupt for the DOS functions, file and memory management functions, or the Hex13 interrupt for the BIOS disk handling functions. Linux, there is the Hex80 interrupt for the system calls. On Windows, there is nothing. The shellcode has to get it for himself. So, to understand how it happens, let's see why is it so different for a shellcode from a normal program. When a normal program is loaded in the memory, and for example, wants to execute a Windows API call, like creating a registry key, this example was taken from a very simple basic notepad exe. In this case, this call is an indirect call. It reads the content of this memory location, this location in the file, and whatever address is stored there, it will be considered as the address of the create key registry function. These addresses are stored in an import table in the executable, and the import table will contain the addresses of all the imported functions. Initially, during link time, it is filled up with some values that are characteristic for the link environment on the operating system where it was linked. Now, when it is loaded into the memory, it is absolutely guaranteed that the Windows DLL files and the Windows API functions will not be found on the same address that was on the development environment. So it has to be resolved. It is resolved by the operating system loader. When a loader loads an executable, it will look up the import table, look up which Windows function, Windows libraries the executable wants to use. It loads these Windows libraries into the process space of that executable and looks up which of the particular functions are going to be used from that DLL file, and looks up the memory addresses of these functions and fills up the import table with those values. So in this case, this link time value will be updated to the runtime value. So when a program wants to execute this API function, it will be updated to reflect the exact conditions on the run environment. Additionally, in case the program is relocatable, which means it could be loaded to some other address than what the author imagined for it, the absolute memory references are stored in a relocation table, and it will be fixed up to reflect the different load location. Now, when a shellcode is executed in memory, none of this housekeeping is present or available. So it's just a block of code. Of course, somewhere in the background, since this shellcode was executed because WinWord was exploited, so it's running somewhere in the WinWord process space. There is somewhere WinWord, there are the Windows DLL files loaded by WinWord somewhere in memory. It just has to be found and located. And how it is done? It is done by using undocumented internal Windows structures. Now, this is where it gets very swampy. So, every process and thread has some global information structures, say the thread environment block. It is pointed by the FS selector register, so it is available also for the shellcode since it's running the WinWord process space somewhere. Now, normally, if you're interested in some Windows programming topic, you would go for MSDN for further information. MSDN is a great source for information if you are following the canonic programming way as Microsoft imagined how you should be programming Windows. If you want to use internal functionalities, then you're on your own. For example, the thread environment block is specified like this. It's an internal structure, don't care about it. Actually, it has a little more granular structure than that. there are two very important pointers that are used. The one is stored in FS18 offset. It is a thread information block. And at FS30 offset is the process environment block. These are two values that were used for reaching to the Windows DLL files. Both of them were used back at the runtime executable packers, but the process environment block turned out to be more standing the test of times in the sense that if a structure is internal and undocumented, it is going to be changed over the time. And this was the least frequently changing of the two of them. So you get to the process environment block. Now, go to MSDN documentation, how it looks like. You see a lot of reserved and unused fields in the structure. If you see a specification that has reserved and unused in it, you should know that at some point they may have thought that it's not going to be used or reserved for from further use. But since then, they evidently used it, but didn't care to update the documentation. And indeed, most of the fields are actually used. But the only important one is the loader data structure. A loader data structure, going forward in the documentation, contains an order module list. Order module list, and we are getting there, we are almost there, is a list of loaded Windows DLL files organized into a linked list. Now that's what we need. We need to get to this list. We need to walk through this list to the DLL file, the particular DLL file we need for its export, and that's it. Now, again, it is sort of a reserved fields in this structure. If you go through to other sources of information, it turns out that there are actually 3 linked lists of these of the loaded DLLs. Each of them provide a chain of the loaded DLLs organized by different criteria. The first in the order as they were loaded, the second in the order as they are in the memory, and the third as they are in the order as they were initialized. And there is a forward link and backward link in each element of the structure. It is a linked list. So in the loader data structure, you will see 3 pointers, and you can choose whichever of these linked lists you are going to use. Each element of the list is going to be a table describing that particular DLL file. And that's what you need. The information you can get from this table, for example, the DLL base, the address at which the DLL was loaded into the memory, and the name of the DLL. If you have these two, from the name you can walk through the chain and select kernel DLL by comparing the name. And if you know the load address of the DLL, you can navigate to the export table of the DLL and read out the memory addresses. So this is how it looks like really in this structure. There is one thing you have to take into account if you are using this structure. Otherwise, you will be hopelessly lost in understanding the shellcode. The F-links, forward links are pointing to the forward link element of the structure. If you are going through the load order list, it will point to the forward link of the load order list. If you are going through the init order link, it will point to the init order for link of the next structure. It is easy. It makes very easy to walk through the chain. You just read the content and skip to the next one. It is extremely difficult, however, if you want to use the element, the further element of this structure. Because if you are using the init order list, then the address you are receiving is not the first byte of this structure. It is going to be 10 bytes afterwards. So, for example, if you want to query the base DLL name and you are walking in the load order list, it will be at offset 30. If you are walking through the init order list, it will be at offset 20. It's a bit confusing if you are reading shellcodes and you don't understand which particular list it is using. Anyhow, let's go to the Red October case. In this case, the kernel address is located using this, yes, the process environment block, then the loader data and the init order list. And with this loadersd, it will skip to the second element of the list. So at this point, it has the load address of the kernel DLL, and it can navigate to the export table, go through the exported functions in kernel DLL, find the one that starts with get, then continues with roca, so it navigates to get address, and from that point on, it can load any other Windows API function that it needs. I should mention that this method makes an explicit condition that kernel DLL is the second element in the loaded list of Windows libraries. And this is true starting from Windows 2000 up till Vista. On Windows 7, an additional DLL was added to the load chain, a mini-based DLL, and it will completely break Red October method. So Red October will not work on Windows 7, Windows 8, or further on. TravNet, another APT threat using a somewhat similar method based on it, it will reach to the first element of the DLL linked list, which is the anti-DLL list. And after that, once it's done, the further, so for example, kernel DLL is located by a similar method. The anti-DLL is loaded by the assumption that it will be the first element. Kernel DLL is loaded by the assumption that checking the length of the DLL name, it will be exactly the length of kernel 32 DLL, the name of the DLL file. Here it starts with the process environment block, the loader data order list, and then gets the DLL base name and checks if the 18th character of the name is 0. These are Unicode stored characters. If it is shorter than kernel 32 DLL, the name, then there will be, no, if it is longer, then there is going to be further characters in the name. If it is shorter, then, well, the autos comment is, it works every time for me. If it is shorter, then some undocumented structure, undocumented binary data will follow the name. If it is exactly the same length as kernel 32 DLL, then there will be the trailing 0 of the Unicode file name. After that, the functions, the individual Windows functions are not resolved by name. Rather, the method is that it will walk through the entire export table, and it will calculate a checksum from each exported Windows DLL function name, and it will compare to the predefined values that it accepts for a particular DLL name's checksum to be. Plugix that I demoed before has a slightly more complicated, sophisticated method. It will specifically check if the DLL name at a certain position will contain 32, and then the LL at the appropriate position that it should be at in the kernel 32 DLL. So now, Plugix has another very interesting trick. It will obfuscate the entry point, the entry to the Windows API function it is hooking. Namely, it will not enter at the entry of the API function. That was specified in the export table. Rather, it will skip the prologue of the function, and it will enter 5 bytes later than that. And the reason is that if you are using some API hooking or API monitoring or tracing tool to follow what is going on the system, it will place its hooks on the entry of the function. Now, if plugix will enter the function 5 bytes after that, it will bypass the protection, bypass the monitoring tool. This is why we were not able to observe the creation or the execution of the drop DLL file, because the shellcode entered the winexec function after the hook. So it was invisible for that tool. So at this point, I have another demo for you, just to illustrate how can we still debug and examine the shellcode. I should be running this on this laptop. It's recorded instead because we don't have enough time, and it would take about 30 minutes to execute on this laptop, which is not a speedboat. So I record it on my analysis. No? I record it on my analysis computer, and we are going to see what's happening. In a debugger, we are going to load winword.exe. We are going to follow the same way, spy after winword.exe. And then we go to the winexec API function address, and this will be in kernel DLL, and we set a breakpoint, but not at the entry, rather 5 bytes after that. So we know that it will be bypassed by the shellcode, so we will place our breakpoint where the shellcode actually enters. Then we open the infected document, and we will observe what is going to happen. So after we opened it, we ended up in the debugger inside the winexec code. So we go out of the Windows API, Windows function from kernel DLL to find out where it was called from, in the hope that it is going to be within the shellcode. So what my main purpose is to end up at the running shellcode and to able to observe and debug the shellcode. And at this point, we are reaching the exit point into the shellcode. And this is actually the instruction when the instance of Word is exited. And after that, here is the API resolving part of the shellcode. From the addresses, we can see it somewhere on the stack. If we are examining the region, memory region, we will see that here is if you can see the dv22.dll, these are the file names that are used by the shellcode. So we ended up in the middle of the shellcode. We can debug it from there. We can analyze the shellcode from there. So another question great question for the shellcode is, where did I come from? What was the hosting document where the shellcode was executed from? And the sole reason is that the executable payload is, I have a lot of content, so if you give with me, we will see what happens if I overtake the presentation by 10 minutes. We know what happens at 0, at -1. Let's see what happens in -10. So anyway, the original carrier document has to be located because the embedded payload is there. It has to be extracted in order to be executed. The one way it is used is, again, from the plugix samples, is enumerating the open handles on the system. Handles are integers by an increment of 4. They can represent different objects. They can represent semaphores, events, directories, registry keys. Some of these handles represent open files. And one of the open files will have to be the hosting document that is just being opened by Word. So what this code does is, enumerates all the possible integer values for a handler and checks by get file size if it's by any chance an open file and the size of the file matches what the shellcode thinks is the carrier document size is. Another method, it's used by Rusibia. The first method was trying to locate the disk file that is hosting the shellcode. The shellcode, but more importantly, the payload. The second method is trying to find itself in memory. So what it does is searching through the memory blocks that are readable for the shellcode. It is checked by is-by-read PTR API function. If it is the carrier document is opened by Word, it has to be somewhere in memory. If it is somewhere in memory, it has to be readable by the shellcode, which is spawned by the WinWord process. So it will look for characteristic bytes within the memory image of the shellcode. These bytes are 51, 51, 79, 79, and 93, 93, D2, D2. So you see, in the RTF file itself, it is in ASCII representation, but it is not looking for ASCII representation. But that is also a line break between them. It is not looking for that. It is looking for binary representation. Clearly, it is looking for the memory image. When loaded into memory, WinWord will convert this ASCII representation of the embedded object into binary. So that's what it is looking for. And an even more sophisticated method, and I was kind of bored with all the schematic methods used by the shellcodes, and I was happy to find Genicab, which was using a different method. It is using undocumented Windows system calls just to solve the same problem, to find out which memory blocks are readable and look for marker bytes. And if the marker bytes are found there, then from that location, it can start to decrypt the embedded payload content. Now, this shellcode part is actually has support for 64-bit systems. So if a WinWord is running within on a 64-bit system, this shellcode can does have a different syscall to support that operating system. However, it is less from being original because it is using a public 64-bit subsystem egg hunting code. This code was published 3 years ago. It is available on the internet. And if the Genicab authors were creative, they were only creative in being more brave in integrating public domain information into their code. I can go 40 minutes from here. Okay, so first the conclusion is, what I have found in this case is that, you see, in each of these three main stages of a shellcode operation, I showed you 2 or 3 typical cases how the shellcodes are solving it. And it was not because, but it was, one of the reasons was because I didn't have more time in the presentation slot. The other reason was that there is really nothing much more. So the targeted attack authors in the most crucial component of the attack, they are just reusing very old methods, very same methods, and very schematic methods. Only these couple of methods are being used in the presentation. Yesterday, Boldy mentioned that Miniduke attack could have been stopped if Microsoft's EMET mitigation tool was installed. I can make an even stronger statement than that. Just recently, secure researchers published a study when they investigated that simple tools. One of them was EMET, the other was like application sandboxing, like using a tool like Sandboxy to restrict WinWord from not executing from the temp folder or not downloading and executing files from the internet. And they were looking pretty much the same 1,000 targeted attack samples that I have analyzed during the past year. And they measured what ratio of the attacks could be stopped if the, let's say, application sandboxing was applied. So I'd like to ask the audience, who of the audience thinks that the block ratio would be above 71.8%? Okay, one hand. Who thinks it's below 71.8%? So the vast majority thinks it's exactly 71.8%. And you're wrong because the exact ratio is 100%. Each and every one of these attacks could have been stopped by application sandboxing. Moreover, each and every one of these attacks could have been stopped by EMET. And this just shows that the authors of the targeted attacks, they can be pretty sure about their target audience. And their target audience are not using these tools. They are not patching their systems. And they are very vulnerable to these attacks. So you could say that, okay, I might use these mitigation tools, but then the targeted attack authors will try harder and they will break into my system anyway. That part is true. But these document exploitation methods are picked up by the ordinary computer cybercrime criminals as well. Over the past year, we started to see that phishing attacks involving Zeus Trojan samples are using document exploitations. And they are using the very same methods, very same shellcodes. And they don't care about each and every particular victim. They only care if like 20% of the victims remain vulnerable. So be smart and don't be in that 20%. Harden your system. Thank you very much for your attention. I would have a couple of more demos, but there is no point continuing because the show has stopped. Thank you. If you have questions, find me.